So we're going to try to talk about some rules for derivatives tonight. There's something funky going on with my computer, so some of what I'm writing is not showing up, and I don't know why, but hopefully we can get through this as it is. So the first rule for derivatives is called the constant rule. You can read it here, and it just says the derivative of a constant is 0, and all that means is if I start it with a function, let's say f of x is 5, then f prime of x is 0. That's all we're saying. And it makes sense because if you think about what is the derivative, it's the slope of the tangent line. Well, if you have a flat horizontal line, the slope is 0, and it's always 0. So it makes sense. But how do we prove it? And so here's how we prove it. We start off with our function, f of x equals c, and we take our limit definition of the derivative, and we plug in our values. Now, there's no x in here, so f of x plus h, we're supposed to replace x with h, or sorry, with x plus h, but there is no x to replace, it's just c, so that's c, and that's c, and because of that, you get 0 on the top, and that means you have 0. All right, so that's the derivative of a constant. The second one we want to talk about is the power rule. So what the power rule says is that if the function is f of x and it's equal to x to the n, so x to any power, then the derivative of that is you bring the power down in front. So you kind of go down there like that, and then you subtract 1 from the power. Okay, that's the rule. So I'm going to show you an example of that. If I want to take the derivative of x to the 5th, it's 5x to the 4th. Bring the power down, and then subtract 1 from 5. So this is 5 minus 1, and we brought the 5 down. If you look at the square root of x, as another example, that can still be written as a power. Just write as x to the 1/2, so then it's 1/2 x to the minus 1/2. Okay, and if you reduce that, I'll go down here for a second, it becomes 1/2 x to the 1/2, and then it's 1/2 root x. Another example is the inverse, so 1/x. You can write that as x to the minus 1. You do your power rule, you go minus x to the minus 2, and then you can write it as minus 1/x squared. So that's the power rule. The question is, how do we prove it? Okay, so let's prove it. I'm going to try anyway. So we're going to start out with our f of x is equal to x to the n. So then our f prime of x becomes the limit as h approaches 0 of f of x plus h minus f of x divided by h. I apologize for these weird lines, but so what we're going to do is we're going to plug in, and we're going to get limit as h approaches 0 of x plus h raised to the nth power minus x to the nth power divided by h. And then what we're going to try to do is we're going to try to expand x plus h to the n. So to do that, we have to think about Pascal's triangle. We know Pascal's triangle looks like this. 1, 1, 1, 1, 2, 1, and then it's 1, 3, 3, 1, and then 1, 4, 6, 4, 1. And what I want you to recognize is the pattern is this is x plus h squared. This is x plus h cubed. This is x plus h to the 4th. So the pattern is the first number is always 1. So when I expand this, the first term is going to be 1x to the highest power, and h gets the lowest power. The next number, you notice, is always a power. So when it's squared, the next number is 2. When it's cubed, the next number is 3. When it's 4th, it's 4. So the next number, the next coefficient is going to be n. And what happens is x goes down by 1 power, and h goes up by 1 power. The next term, I don't know any of these terms in the middle, but I know they all have h squared and then h cubed and so on, all the way up to, you'll notice the last number is always 1. So when I expand this, I'm going to get x to the n, I know that. The next term is going to be nx to the n minus 1 times h. The next term, I don't know what it is, but it has at least h squared in it, okay, all the way up to h to the n. And we're going to divide by h. So what happens is this x to the n cancels with that minus x to the n. And that gives me then the limit as h approaches 0 of nx to the n minus 1 times h plus a bunch of terms all with h in them all the way up to h to the n divided by h. So what happens is I can factor out an h. Okay, I can take a limit as h approaches 0 of h multiplied by n x to the n minus 1 plus dot 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 plus h to the n minus 1. So what I've got is a bunch of terms all still having h in them. This term does not have h in it, and it's all multiplied by h. So what happens is these cancel, and when I let h go to 0, all of this has h in it. There's an h in every single term, which means they all go to 0. And what I'm left with is that. Okay, and that is the proof of the power rule. So I showed you a few examples of it. That's the proof of it. Okay, the next rule is the constant multiple rule. Constant multiple rule says if you have a constant multiplied by a function, the derivative of that is just the constant multiplied by the derivative of the function. So for example, I have 2x to the 5. It's just 2 times the derivative of x to the 5. X to the 5, we use the power rule to get that. And then it reduces down. Okay. Here's the proof. It's fairly simple. We start with our function f of x. So if our function is c times f of x, then for f of x plus h, we just put wherever there's an x, we put an x plus h. So that's our function x plus h. So that's where I'm getting these terms from. And then you'll notice that c here and c here means I have a constant factor, or a common factor, sorry, of c. So I can take it out. And since it's not affected by the value of h, it's constant. It doesn't change. I can leave it out of the limit. So what I can do is I can put the limit in with the f of x plus h stuff, because that is affected by what h does. Constant is not. The constant, if that's 5, that's 5. It's not changing. It doesn't matter what h is approaching. And so I end up with my proof. So there's the constant multiple rule. All right. So what does that look like in practice? Well, we saw one example there. Let's just do another one. I thought I might have another one on the next page, and I don't. But let's just do another one. Let's say I gave you f of x is 3x to the 4th. So that becomes, leave the 3 out, do the 4x cubed, because that's the power rule, and it becomes 12x cubed. And you're probably noticing that that really ends up just getting multiplied by that. So you can do that directly. So if f of x is 10x to the 6th, then that just becomes, the derivative becomes 60x to the 5th. You can sort of skip this middle step here and just multiply. When you bring the 6 down, you just multiply it by the 10. Okay? So that's the power rule, that's the constant rule, and that's the constant multiple rule. So the last rule that I want to talk to you about for now is the sum and difference rule. So the sum rule says if you have something plus something, a function plus a function, and you want to take the derivative of it, you just take the derivative of each of the two functions. Difference rule is the same. So here's the proof, okay? And you gotta stay with me. I'm gonna look at this function, okay? Whoa. So when I put in x plus h, I just put in an x plus h in here, and an x plus h in here. So that is where this is coming from down here. Okay, that's what I end up with. So this is f of x plus h. This is f of x. And I know it's kind of confusing because there's already an f of x in it, but this is the function with h plugged in. Well, x plus h. And this is the function without x plus h plugged in, just with x. And what we're going to do is we're just going to remove the brackets, and we're going to just put f of x plus h minus f of x together, and minus g of x plus h plus, because minus and minus, g of x. And all I do then is I change this sign. So I take the negative out, and then I can say this piece is one term, and I just put it by itself. And this piece, with the h included, because it's still divided by h, is the other term. And so that's that piece. And that is f prime of x, and that is g prime of x. So that proves the difference rule, and the sum rule is very similar to the proof's exactly the same. Okay, so here's an example, just to sort of show you how this works. This is a sum. To get y prime, I just take this term by itself, this term by itself. In this term, I have a constant multiple. So the 3, I'm doing this in very careful steps. So the 3 stays out, and then we apply the power rule to this. So we bring the power down, 2, and we subtract 1 from the power. That's where we're getting the 1. We do the same thing here. The 4 follows because of the constant multiple rule, and x cubed, we use the power rule, bring the power down, and subtract 1, we get 3x squared. And then we just multiply that out and get 6x plus 12x squared. We can jump directly to here. I'm just emphasizing the steps, but you can quickly go through the steps if you wish to. Okay, so here's another example. So 3x to the 100, that's 300. X to the 99. Okay, 2x cubed becomes 6x squared. The 5x to the 10th becomes 50x to the 9. And then at the end, this guy is a constant. And we said the derivative of a constant is 0. So that is why there's technically, I guess, if you want to write it in there, a plus 0. But we don't have to write it because it's 0. So that's why we end up here. So those are the derivative rules. We're going to practice a lot more of them. But those are the derivative rules, the shortcuts so far. There are more. We're going to do more. And the question always is, do I have to know the proof? No. You just have to know how to use them. And we will practice more of them